Alright guys, in this video we're going to be going over an AP Physics 1 free response question that was publicly released, and it's dealing with Unit 4 content, energy conservation, work being done in a lot of different ways. So let's get into it. It says, a block is initially at position 0, right here, and in contact with an uncompressed spring of negligible mass. The block is pushed back along a frictionless surface from position 0 to position -d. So the block is moved back here and compressing the spring, as shown above. Compressing the spring to an amount of delta x equals d. The block is then released at x equals 0, or position of 0. The block enters a rough part of the track. So everything in gray here is a rough part of the track. Everything white here is frictionless. And eventually comes to rest at a position of x equals 3 times d. And so it's compressed a distance of d, it accelerates and speeds up to this position, and then it slows down eventually, reaching 3 times the distance it was initially compressed. It says the coefficient of kinetic friction between the block and the rough track is mu. So eventually this question is going to be asking you about the energy that's going on for the block and spring system. So just in general up here I kind of sketched out how do we think about this. So for the system as a whole, the block and the spring, at position 0 in the very beginning there's no energy that the system has. When the person is compressing the spring, they're doing positive work, but they're increasing the spring potential energy of the system. And they're releasing the block from rest, and so at this position it's got spring potential energy only. By the time the block reaches here, all that spring potential energy gets converted or transferred to the kinetic energy of the block, and so it's just got kinetic energy. And then as it slides, that kinetic energy gets less and less and less and less and less, and it eventually goes to 0 because it stops moving. Well, where did all that energy go? The system's energy is decreasing over time because friction is doing negative work on the system. The block is sliding to the right, and it feels a frictional force back to the left, which can be expressed like this, right? The change in kinetic energy from this position to the final position is equal to the negative work being done. Kinetic energy is decreasing, which is just the negative force of friction times the total distance that it moves, and in this case it moves a distance of 3d. Okay? So part A asks, on the axes below, sketch and label graphs of the following two quantities as a function of the position of the block between x equals -d, where it starts, where the spring is fully compressed, and the final position of 3d. It says you do not need to calculate values for the vertical axis, but the same vertical scale should be used for both quantities. So what are we graphing? So we're graphing how energy changes as a function of position. Right, here's our 0 position, here's the position of the full compression, there's its final position, and we're graphing, number 1, the kinetic energy of the block, and number 2, the potential energy U of the block spring system. So we've kind of talked about the energies already a little bit. At position 0, the spring is uncompressed, so there's no potential energy. So we're going to put the potential energy of the system in blue and the kinetic energy of the block, or the block spring system, in red. So when the spring is uncompressed, it has 0 potential energy. And as the spring is compressed, it has more and more spring potential energy, right? And it's going to have its maximum spring potential energy when it's the most compressed at -d. So how do we think about the shape? Like, we know it's got 0 spring potential energy at a position of 0, and when it's at a position of -d, it has its maximum. But like, how do we know that? We know that it decreases as the spring uncompresses, but like, is it linear? Is it nonlinear? Well, we've got to go to an equation that tells us how the spring potential energy of a spring changes as the amount it's compressed or stretched changes. So it's just US equals 1/2 K times compression squared, or stretch squared. So we can see that the graphical relationship between the position of an object and the spring, or sorry, the compression of a spring and the spring potential energy stored by that spring is kind of parabolic in shape, because spring potential energy is proportional to the square of the compression. So as the spring is uncompressing from negative d at maximum to 0 at a position of 0, when the block reaches a position of 0, it's going to change kind of in that quadratic or parabolic shape. Once the block gets to position 0, and as the block moves farther and farther as it's slowing down, the spring potential energy of the system is just 0, because once the block gets here, the spring is uncompressed and it's not compressed anymore, so it kind of zeroes out here and then just stays 0. Well, what's true of the kinetic energy of the block? Well, in this region right here, and this is only going to apply to the region between negative d and 0, we need to think about the fact that the total energy of the system, because the block is on a frictionless surface, it's always going to be, spring potential energy plus the kinetic energy. That stays constant because there's no negative work being done for the first amount of displacement. That's all happening on a frictionless surface. So only this will be true where if we add up the spring potential energy and the kinetic energy, the sum of those two things has to be equal to the same value, right? So when we're looking at this right here, if we first graph the shape of our spring potential energy, we know that here at position D, there's no kinetic energy, it's all spring potential energy. Well, what about, let's say here, there's 2 bars of spring potential energy, and there has to be a total of, the beginning, 1, 2, 3, 4, 5, 6. So at any point, the total energy has to be 6 bars, essentially, of energy, or 6 vertical grid spaces. So if here, the spring potential energy is 2 bars, that means, I didn't get that quite right, that means the kinetic energy has to be 4 bars. Or if, let's say here, here the spring potential energy is 1 bar, that means the kinetic energy has to be 5 bars. And I'm a little off here, but you can kind of see that essentially the shape of the kinetic energy will be a vertically mirrored image of the spring potential energy. But that is only true for the spot where there is no friction, right? So once the block gets to the zero position, all the energy is kinetic, none of it is spring potential energy. But once that block starts sliding across this rough surface, the kinetic energy is going to decrease because there's negative work being done. So we know the kinetic energy will be 0 at the final position, it's maximum at a 0 position, and it's going to decrease from the 0 position to the final position. Now, the question is, what's the shape? We kind of answered that question for spring potential energy here. Well, how do we figure that out? We had to identify a relationship, some kind of equation that told us the relationship between spring potential energy and position. Well, we can do that for kinetic energy and position. And that kind of comes from understanding that the kinetic energy will change by the amount of the work that is being done. And the amount of work that's being done is equal to the frictional force, which is constant throughout the sliding, times the distance. So if you slide, let's say, 1 unit of distance, you're going to reduce your kinetic energy by a certain amount. If you slide 2 units of distance, you're going to reduce your kinetic energy by double that. If you slide 3 units of distance, you're going to reduce your kinetic energy by 3 times. You get the picture, it's changing linearly. And so it's going to be a linear decrease of kinetic energy from a position of 0 to that final position of 3D. Okay, the next part says, the spring is now compressed twice as much to delta x being 2d. Remember, initially it was just d. So the student is asked to predict whether the final position of the block will be twice as far at x equals 60. Remember, initially it only went to 3d, so they're saying we're compressing the spring twice as much. The student is asked to predict, will it travel twice as far? Will it reach a final position of 6d? The student reasons that since the spring will be compressed twice as much as before, the block will have more energy when it leaves the spring, so it will slide farther along the track before stopping at position x equals 6d. So in part B, we're thinking about what part of the student's reasoning is correct and what part of the student's reasoning is incorrect. So the first part asks, which aspects of the student's reasoning, if any, are correct. Doesn't mean there are correct. It's just if there are, let's identify it and explain how you arrived at your answer. Usually when we have these kind of problems on the College Board, there's something correct about a student's reasoning, something incorrect. So when the spring is compressed twice as much, the block will have more energy when it leaves the spring. Like that's part of what the student reasoned, and that is a correct part of the reasoning. Because remember, our spring potential energy equation is equal to 1/2 times the spring constant times the stretch squared. And the spring potential energy the system has in the beginning is all transferred to the kinetic energy the block will reach once it reaches that position of 0. So if x gets bigger, spring potential energy gets bigger, therefore the maximum kinetic energy of the block will also be larger. So you can say that when the spring is compressed more, it will store more spring potential energy, which gets transferred to more kinetic energy when the block reaches a position of 0 and the spring is uncompressed. So that is a correct part of the student's reasoning. The second part asks, which aspect of the student's reasoning, if any, are incorrect? And again, explain how you arrived at your answer. So remember, the student predicted that the spring, when compressed twice as much, will essentially lead to that block reaching a twice as far final position. So instead of stopping at 3D, it's going to stop at 6D. Well, that turns out that is incorrect. So the student is incorrect that the block will travel twice as much as before, since the spring potential energy is proportional to the amount of compression squared. Remember this equation up here? So if you double that, that's going to not double the initial spring potential energy, that's going to quadruple. It's going to go up because it's a squared relationship. Doubling the compression will increase the initial stored spring potential energy 4 times, which will lead to a 4 times greater kinetic energy that the block will have at position 0, and consequently lead to a 4 times greater final position. So it's going to go 4 times farther, not just 2 times farther. So that's kind of conceptually or qualitatively thinking through the rationale. Part C asks to use quantitative reasoning, which includes equation as needed, to develop an expression for the new position of the block. So up here we kind of reasoned through that it should be 4 times greater, and this is going to be, I guess, using an expression or an equations to show that it will be 4 times greater. So if it originally slid to a final position of 3D, this should essentially show that we get to a final position of 12D. Okay, and we've kind of talked through these energy equations already, but just in general, we'll go back. So the maximum spring potential energy is 1/2 times the spring constant times the initial compression squared. That all gets transferred to the maximum kinetic energy at position 0. That all gets taken away by the negative work caused by friction, which is equal to the work done by anything is equal to the force, or the work on something is equal to the force it feels times its displacement, right? Or the negative work done by friction is equal to the force of friction that the block feels times the total distance the block moves, which will be equal to the final position it reaches, because it starts at a position of 0 when the negative work is started. So we take 1/2 kx squared equals this, the force of friction times the displacement. This is the amount of negative work done. This is the initial amount of spring potential energy. Now, we could use this equation right here just to do a little proportional reasoning, kind of like we did up here, and I'll save that for part D. But I'm going to show you, like, maybe this is a little bit too exhaustive, but how you can go through using a symbolic expression like this to get our final distance right there. Now, they don't give us the spring constant, and they don't give us the size of the frictional force, but in the original scenario where the compression is just D, and the second scenario where the compression is 2D, the spring constant and the force of friction are the same, right? And so I'm using this expression right here to actually come up with an expression for the ratio of the spring constant to the force of friction, because whatever that is in this first scenario will be the same in this scenario. So if we have 1/2 kx squared equals the force of friction times the final position, the original compression is just D. the final position the block reaches is 3 times d, right? So we know that when it's compressed an initial amount d, the block will reach a final position of 3d. So given that information and this, I guess, energy conservation equation, we should be able to find an expression for the ratio of the spring constant divided by the frictional force in terms of d, right? So I just divide each side by the force of friction. Well, actually, divided first each side by d. So d cancels out here. One of those cancels out over here. Then I divided each side by the force of friction. And then I multiplied each side by 2. And we get that the ratio of k divided by the frictional force is equal to 6 divided by d, right? And that is going to be the same no matter how much the spring is compressed. So let's now go back to our equation right here that we came up with for our new scenario. So actually, before we do that, I'm going to solve this expression for the final position, because remember, we're trying to figure out how far the block is going to slide and put it in terms of d. And so if I just divide each of these sides by the frictional force, it's going to move the frictional force. It'll cancel out on the right side, move it over to the left side. We get this, that k divided by the frictional force times the compression squared divided by 2 equals the final position. We're just solving like this energy conservation equation for final position. So we get this, right? Final position equals the ratio of k divided by the spring constant divided by the frictional force, multiplied by the compression squared divided by 2. For the second scenario, remember that delta x is 2d. It's not d. And remember, we just found out down here that the ratio of k divided by the force of friction is 6 over d. So we just substitute that in there. And if we square 2d, we get 4d squared. And then we can cancel out one of the d's in the denominator, one of the d's in the numerator, so we're just left over with d. And 4 divided by 2 is just 2. So we get that the final position is equal to 6 times 2d, or the final position is equal to 12d, right? Which, remember, the original final position was 3d, so that is 4 times farther than the first scenario. So in the last part, we kind of just use a quantitative answer or symbolic answer quantitatively using equations to basically back up what we were saying about the correctness and the incorrectness of the student's reasoning. But the last part here, it kind of wants us to explicitly link some part of our, what they're calling quantitative solution here, with what we just talked about qualitatively up here. So they just want us to kind of reiterate so that they know we see the connection and we can see how the quantitative answer is backing up our qualitative answers. Okay, so it reads, the last part, explain how any correct aspects of the student's reasoning identified in part B, that's the qualitative part, are expressed by your mathematical relationships in part C, that's the quantitative part. Explain how your relationships in part C correct any incorrect aspects of student's reasoning identified in part B. Okay, so we're basically explaining how our equations show that the student is correct and how it corrects any incorrections. It says, refer to the relationships you wrote in part C, not just the final answer you obtained by manipulating those relationships. Remember, our final answer was that the final position equals 12d. So we have to kind of go back into, how we got to that final answer to back up what we said about the qualitative reasoning of the student. So let's first start with the correct things. So in part C, the equation that the maximum kinetic energy is equal to the maximum initial spring potential energy, which is found by 1/2 times the spring constant times the amount of stretch squared, shows that when the stretch, the delta x, the compression is increased from d to 2d, that the maximum spring potential energy is going to go up, and therefore the maximum kinetic energy the block will have will also increase. So as delta x gets bigger, spring potential energy goes up, and therefore kinetic energy goes up. That's right. That was a correct aspect of the student's reasoning that we talked about already in part B. Okay, now to correcting incorrect assumptions about the student. And remember, we said the student was incorrect in that the block will not slide twice as far as the original amount. We said it's going to go farther than that. So, and this is that proportional reasoning I was talking about, which we probably could have done for the quantitative aspect as well. So it says the equation 1/2 kx squared equals force of friction times the final position. Remember, this is the initial spring potential energy is the same as the total amount of work done by friction. That's what this right side of the expression shows. Solved for the final position, which we had in the previous part, where final position is equal to 1/2 times the ratio of k divided by the frictional force is equal to delta x squared, where delta x is the initial compression of the spring. This equation corrects the student's reasoning, showing that if the initial compression is twice as much, this guy is twice as big, that means the right side of the equation will be 4 times bigger, because if you're squaring something 2 times bigger, that's going to be 4 times larger, which means the block will reach a final position that is 4 times greater. If the right side of this equation gets 4 times bigger, that means the left side of the equation also has to get 4 times bigger, which means the block is going to reach a final position that is 4 times greater than the original position, not 2 times the original final position that the student initially reasoned.